dive in. This is just introductions. Background, again, pretty much generic. This is mostly about test experimental apparatus that's a work in progress. Some tests have been done, but more are to go on. And maybe the fundamental thing is this is to support a project funded by the NLSI to create discrete element models for predicting excavation or other soil mechanics kind of operations. So this is kind of an enabling or supporting function. Okay, this is something about motivations. I guess something that I don't know how well people realize is soils have no equation of motion. There's no first principles equation of motion like Navier-Stokes for fluids or solid mechanics. And as a consequence, it's very difficult to predict. You don't have an equation of motion says that you can describe something over time, and you don't have that with soils. So normally there's a whole lot of field testing followed by some kind of model, more heuristic kind of model development, and you go back and forth between the two. In the space environment, you do not have the opportunity for field testing. You've got to be able to predict, hopefully from some kind of first principles knowledge of what's going to happen for a machine or flow of material or something like that. So that's my summary of motivations. Previous work, Surveyor 3 and 7 had a little backhoe-shaped scoop on it, and there was only one measurement that was ever published from Surveyor 7. Surveyor 3 had some motor current problems or motor bearings seizing up, and so the results from that were not conclusive. Surveyor 7 had a bunch of both trenching and pressing a flat plate into the surface, but only one of those was ever published. And there was the ALSEP was talking about chasing data, and you have a similar problem chasing surveyor data. Data is just flat out lost. These others just describe a bunch of work that's been done to motivating work. This here was our example of trying to reproduce that surveyor. It was called a bearing test. So the front of this scoop has a little bit of a flat plate there. And this was a small bed, and so we're actually going to reproduce this in a bigger bed where the boundary effects are not there. It's just a lot of experimental details. I'm not sure that you want me to grind on them. Here is results. This is the actual bearing test experiment. This is the data from measured in situ on the moon, and this is the measured data for the, I got to read it myself here. Okay, yeah, different angles of tilt of the bucket. 70 degrees was the best we could figure out was the angle of tilt of the bucket with respect to the horizontal of the surface, and he did 65 and 60 as a comparison, so they're all bundled together there. Then this was a trenching experiment, although we had nothing on the moon surface to compare to, but we did that trenching, and this is in a loose soil case, and this is in a compacted soil case, which shows a bunch of intermittent kind of failures going on, which is a common phenomenon in soils. The next is we're beginning to describe the large soil bin facility. It's 2 meters by 6 meters long, interior volume, 60 to 70 centimeters deep, and we fill a half of it. One of the things, the challenge is the mess you make is so you fill a half of it and you can refill the other half and you can create your soil beds back and forth. This bin has large inertia, very stiff structure, mounted on a very stiff plate. The issue, if you're doing load cells to measure things, you want to have low structural resonances that are not good, that push them out of the spectral range, or you just want a low noise level coming from anything else for your load cells. We created a cheap lunar soil simulant of silt and sand, and lunar regolith is described as a silty sand as a soil classification. And then this just gives more information there about the control parameters. A key thing is that we use a single 6-axis load cell. Many of the demonstration experiments that we've worked with, developed by others, is they'll put a bunch of linear load cells at different locations on the instrument, and you get crosstalk, structural things, you get moments that you lose. Your free body diagram can get very messy, and trying to turn those linear values into the true values that you're looking for. So a 6-axis load cell really solves that problem, but it's an expensive way to go. This gives you sort of the 3 meter by 2 meter load cell, the rails that propel along, a bucket in place, a vertical actuator, and I guess don't need to say more about that one. This is a little bit more detailed in the same thing. This gives a rake and a grading blade. Again, preparing repeatable soils of consistent strength is a challenge, and that's one of the ways, sort of a cheap way to do it. And this does show, I don't know if you see it that well, some faint laser lines. That's related to their laser sheets, and the intent is to be able to get the surface profile of the soil. So you get soil deformation along with the forces on the bucket, all of which are valuable to then try to model with a discrete element model. This is just giving some of the test parameters that were both used before in the small 1-foot soil box and in the large soil box for the surveyor, reproducing the surveyor thing. We picked the surveyor bucket because it's a little 2-inch wide bucket, backhoe shaped thing, and for DEM, keeping things small is handy for computational. This is just more aspects. I talked about the 6-axis load cell. We actually have 3 load cells, one that has a smaller range to it, probably less useful. These are the 2 most useful ranges of the forces, vertical and transverse forces. And the moments will just be we'd have to know the moment arm, but I don't know if anything else to get out of this. Okay, density measurements, that's another aspect of soils. We list a bunch here that we've done. One would think this is basically measuring the AC impedance of the soil, and you have an AC model for the soil, and from that you can get both moisture content and mass density. We found that at low bulk densities or near low relative densities, a few percent relative density, that it really didn't work well at all. And I think it has to do with you now got a surface impedance effect that you don't get with a densely packed soil. You know, an additional term in the AC model for the analysis. And this is usually used on construction sites where they're really trying to pack it down. So they look at the high density end most of the time anyways. This is an ASTM standard method. You basically excavate a hole without disturbing the remaining material. You let a water-filled balloon go down in, and you measure the volume of the water that went in. Nice method, but it's really hard, again, on the low-density soils of not disturbing the soil, not compacting it. Shelby tube, that kind of disturbs at both ends, because as you're pressing that, it's just a hollow tube. You put it in there as a known volume, you fill it up uniformly, and you weigh it. Simple in concept, but you disturb the soil where you're chopping it in. And we sort of seem to saturate at below, like at 60% relative density, and on the low end, I guess we haven't really studied at the low end, but it's certainly going to mess up the soil. Okay, and that's I guess I summarized all that in the bottom. Cone penetration, this is basically a quasi-static, slowly penetrating, steady penetration cone. I found it to be the most repeatable, highest quality measurement. It still has problems in terms of turning that into engineering properties like soil cohesion, soil friction angle, wall friction angle, bulk density. It's in principle capable of doing that, but when you really start using, and there's only been a couple of models that have been developed well enough that you can use it as a parametric fit as a function of depth. Because you got this nice set of data, if you got these forces as a function of depth, if you can fit it to that, you're really doing well. So this is just telling us what the fitting does. You get some nice R-squared factors, but it's tricky. The solutions are really not unique because there's a poster over there. Maybe let's just refer to the poster. This is the equipment. There's a poster, I think it's E17 or somewhere, or E10 or something like that actually describes the penetrometer a lot. This is an example of in the new soil bed. This is JSC 1A as a soil. This is some penetrations that have already been done. So they pushed it in there, they moved away, pushed it in there, pushed it in there. So it's a way to get multiple measurements out of the same bed. I think, I would argue with my colleagues that, that's a little bit too close together to be penetrating. Again, the laser lines represent the laser sheets. We can track deformation as well as picking up the components of the force on the bucket. This is the measured data from those exact tests. You do see repeatability. And this is a loose soil case. I don't know what else. Some ways okay, this heat profiling, I've sort of referred to it a number of times. I don't know if I need to spend more. But this represents an actual image. We have to calibrate. Each laser line has a calibration sheet of targets so that we can turn pixel addresses in the image into XYZ positions in physical space. And that's a bit of a tedious calibration. There are some fancier ways at $70,000 to $100,000 to buy, digital coherence type processing of images. They're sort of like stereo imaging, but it's using correlation phenomena between pixels, but that's out of the budget, so we're doing a cheaper method. This is results. This is just pictures of buckets in motion. Okay, this is the excavation forces from that particular run. This bucket is really one that was built for Johnson and a small rover excavator, so it's kind of like a front-end loader bucket. And conclusions. I don't know. I guess I want to. How easy is it to play that video that we had on here?
We can switch pretty quick.
You guys can read the words in the meantime here. Let's see, it's at Digger 30 degree. Okay. So this is the real-time stuff. These little dimples are from cone penetrations, but notice the very buckling kind of failure in front of the soil. And so what we can with this is we really can get an XYZ profile of the surface as a function of time during the excavation. There are issues with bucket filling, both spillage out the side and bunching up at the front before it slides back in the bucket, and then the curvature of the bucket back in. The whole paradigm of excavation and the operations is a non-trivial activity, which will have to be optimized in a low-gravity environment. Don't take your Earth-based experience with you. So good enough.
Do we have one or two quick questions? I don't want to not give you the opportunity.
Chaotic enough not to. My boss is going to ask a question.
Do you have any triaxial tests to go along with your penetrometer tests?
For JSC 1A, we have triaxial measurements, but in a lab. I mean, it's this material, but done in triaxial setup. So yes, ring shear, triaxial, compaction, so odometer type measurements.
So how does the presence of volatiles and perhaps stickier soils change what you're working on?
Was the presence of volatiles?
Volatiles, making the soil clumpy and sticky like it was on Mars?
This is done in ambient. It's a fairly dry environment. The measured moisture is like 0.07%, but there's no particular attention to volatiles. This is sort of as manufactured and as it would live sitting in a large room. Now we are starting to do some vacuum stuff, and we'll evacuate that. But soils, the best work I know of is from '67, a thesis of somebody who did some work, and they found at 10⁻⁴ tore, soils got stronger. At 10 to the minus 7 tore, they got weaker as compared to ambient. So there's some interesting phenomena that goes on in vacuum. There was a couple of other questions I saw back there. The lady back there, I think, had her hand up first.
Hi, Lillian Ostrak, grad student at ASU. I guess maybe I missed it, but how are you filling the container? Because I've actually not done experiments similar to this, but I've done some experiments looking at the compaction of a very basic simulant soil, and we know from a lot of Dave Carrier's work that the compaction of the lunar regolith gets very much within the first centimeter. And in some of the work that I've done, I've really noticed that the first centimeter of soil or of my simulant soil is very loose, and then after that, it's almost hard as a brick. So it didn't look, and of course, video is different than actually being there watching this going on. It didn't necessarily look like you were getting that kind of resistance in your setup here.
Right. The beam that propels it's got a lot of horsepower behind it, so it moves pretty smoothly. But as far as our soil bed preparation, our most sophisticated way is a layered approach. It's a very much ASTM standard layer approach, and then you treat that layer with some degree of compaction. You add another layer, you treat it with the same compaction, you build it up that way. You can get almost homogeneous systems that way. This material here, because it's in the metric tons of material category to fill these boxes, we try to fill it layer-wise in the beginning, but then we do that tilling process. So a tilling followed by either a raking and or compaction, a repeatable compaction process is about the best that we can control it. But this here is described as loose. It's just raked with the teeth that go down sort of maybe 5 times deeper than we're going to excavate. And then we follow with just a vertical edge rake to flatten that surface, which does change the surface structure also.
I might have missed you say this, but how do you expect your results to scale with gravity? Is really the strong dependence on, say, density for the force curves, or is there a strong dependence on gravity also?
The gravity is going to come in during the creation process more than during the existence. The moon, what you find is after that first 10 centimeters, it's over-consolidated in a way inconsistent with the gravity. And one of the works that was cited here talked about they did try to look at scaling. There's no simple scaling law to that, and perhaps no scaling law at all. And because of the difficulty of repeatability of preparations, you can get confused as to what you really created at that gravity level. So I would say there's no known scaling to gravity, but maybe it'll be discovered someday.